Welcome to this Friday. I'm Eric Kolachik. I'm director of the Hariri Institute, and I want to welcome everyone to our Did You Know You Could series. We've got a great talk today. I want to put on your radar two other events since I'm not going to be talking for much of this, so I'm going to take my little period here to put a couple other events on your radar. We, of course, have this Did You Know You Could series, and we'll tell you more about some of the other talks later in the series, but two other events we're holding as well are a panel on atypical PhD journeys, where we're going to have a panel of people talking about some experiences that have involved everything from working at national labs to creating startups while doing your PhD. That's going to be on the 3rd of December. And then for any of you who are involved to any extent in clinical trials, a lot of clinical trials across the US and the world in general have been disrupted significantly by COVID. We have a special event on the 7th of December that's going to be talking about some of the statistical implications of when clinical trials, trials on human subjects are interrupted, and what are the implications on some of the analyses that you're going to do. So without further ado, let me just tell you a bit about the series. This is a series aimed at sort of a low bar to entry. It's meant to just give you a sense as to what waits you in a larger space somewhere on a topic that you might not have even known that you wanted to know about. It's meant to be in a non-COVID era, something where we could all sit around a table with our brown bag lunches, meet each other a bit, hear something interesting from a speaker, and then chat more about what the speaker talked about, how it could influence the work we are doing. The series is importantly led by the Hariri Institute Graduate Student Fellows, and I'm very grateful to the fellows for having put together this year's events. The Hariri Institute Fellows Program is a competitive program to recognize PhD students pursuing computing and data-driven research at BU here, and doing a particularly awesome job in doing so. It's a very competitive program. It began in 2017 and has supported 25 grad students so far over the years, and we currently have 18 of them in the program currently. I'm going to turn it over to your host, which is Defne Abur. She's a PhD student in the College of Health and Rehabilitation Sciences. She was appointed as one of our graduate student fellows in 2018. She has a BS in engineering science from Smith College, concentrating in biomathematics. And she performs research in hearing sciences and middle ear acoustics there. Now as a graduate student in Dr. Kara Stepp's Sensor and Motor Rehabilitation Engineering Lab. Her research is focused on examining auditory factors in speech and also using neurocomputational models to interrupt disruptions in the speech. So Defne, I'm going to turn it over to you, and thank you again for putting together today's session.
Thank you, Eric, for the introduction, and thank you all for attending this talk today. Before introducing our speaker, I'd like to first just take a moment to get to know you all a little bit better. And to understand who's here today, I'm going to ask you to participate in a series of questions using the group chat feature on Zoom. So first, I'd like to ask, using the Zoom chat feature, if you could please type your answer. What is your field of study? Okay, so it looks like we've got people from a variety of backgrounds here, which is really exciting. And my next question is if you could please type your familiarity with the topic of today's presentation. So geometric representations of language. So you can write none, a little, fairly familiar, or very familiar. Okay, so it looks like most of us are not too familiar with the topic, which is really exciting. So we have a lot to learn today. And lastly, I'd just like to ask what you hope to gain from today's presentation. All right, so having a general understanding, maybe a broader perspective on natural language processing. So learning more together. Okay, great. So I want to thank you all for participating in these questions and letting us get to know you a bit better. And now I would like to introduce our speaker. And just a quick note that we're going to discuss questions at the end of the talk. So if you could just hold on your questions until the end, or you can type them in the chat window and we'll address them after. So today's speaker is Dr. Derry Wijaya. She's an assistant professor in the Department of Computer Science. She conducts research in natural language processing and knowledge bases with a focus on machine learning and deep learning applications on these research areas. Her studies include machine translation, which demonstrates how to leverage well-annotated languages to improve the translation of less annotated ones. She also studies methods for automatically learning the meanings of verbs and extracting information for knowledge-based population through analyses of diverse information sources. Prior to joining BU, she conducted her postdoctoral research at the University of Pennsylvania, and she has a PhD from Carnegie Mellon University and received her bachelor and master's degrees in computer science from the National University of Singapore. Please join me today in welcoming Dr. Wijaya to talk to us about representing language geometrically as clouds of points.
Thank you, Defne. Should I start the presentation?
Yes.
Okay, let me share my screen. Yeah, so today I'm going to talk about this topic, which is, did you know you could represent languages geometrically as clouds of points? So there's my email in case people want to reach out later after this event. So the slides, I actually took it from Dan Jurafsky's book website. So there's an excellent book on NLP, and he has just recently going to, I think maybe it's already out, the 3rd edition of his natural language processing book. So coincidentally, this was also the book that I used to learn about NLP the first time, long time ago, but that was the 1st edition. So now it's the 3rd edition. And I also take some slides from my students' presentation during one of my class, which is the seminar class on how to extend NLP to many languages. So the question is, to begin with, how do we represent words? Right? So we can represent words using like their definition in dictionary, but that will be hard for computers to process or to do operation or computation on them. So a long time ago, there was a philosopher of language, Ludwig Wittgenstein, in 1953, and also a linguist, first in 1957. So they started this idea of representing words not just by the symbol, like a sequence of characters, but rather in how they are used in the language itself. So the meaning, we know the meaning of a word based on the company it keeps, basically. So if you know these words, say ong choy, appear many times with words like rice and stir fry and green, leafy, you sort of start to know that ong choy must be something like spinach or some sort of leafy vegetable, leafy green vegetable like spinach. And it's true. In Indonesian, we call it kangkung. And I think, but somehow it's called Chinese watercress also. There's another name, but ong choy is also another name. So like, even when you don't know what ong choy is, when you see how it's used in the language, you can sort of infer the meaning of ong choy. So that's the whole idea behind representing words by their usage in the language. And so the words around that word define the meaning of that language. So if two words, say A and B, say spinach and ong choy, they have almost identical environments, we say that they are synonyms, or that they, probably have similar meanings. So this new model of meaning that focus on similarity, you can represent them as, instead of just word like ongchoi, like ONGCHOI, instead of just representing ongchoi as that word or with some index like word 45, we represent them as vector. So now a word is no longer just a symbol, but it's a bunch of numbers. And when we plot these numbers, say in two-dimensional space, for example, here, we can see that words that are similar should be nearby in the space. That means they should have similar vectors or similar numbers in their vector representation. So this is, I think, what it means by the clouds of points. In NLP, we call it embeddings, because we basically embed these words in space, in this word embedding space. And the word embedding encodes the information or the meaning of the words, such that words that are similar are nearby in this embedding space. So how do we construct this vector, right? So we can look at, for example, the easiest way is to see the context in which the word appears in sentences. So for example, the word apricot and pineapple, they appear in sentences like, you know, cooking or baking sentences, right? You have sugar, tablespoonful of apricot, or fruit or jam or pinch. While computer and information, you use also these words in the same context, like programming or study or optimal or data and so on and so forth. So you can see just by looking at these 4 sentences that we can create such a vector just by saying, okay, for each word that I want to study, let's take a look at what words appear around this word. For apricot, it appears around with the word pinch around it, with the word sugar around it. Pineapple also as well, maybe appear 1 time with the word pinch and 1 time with the word sugar. And digital appear 2 times with the word computer, and information appears 6 times with the word data. And so you can create these numbers based on your data, like your corpus, where you find these words, basically. So this is called the word matrix or term context matrix. So these rows are the terms, and these columns are all the words in the vocabulary that we call the context, or the context in which these terms appear in your corpus. So from here we can see that apricot has similar context because they appear with similar words, while digital and information also have the same context. So they are more similar, say digital is more similar than information than to apricot. So if we visualize it, these vectors, so just now apricot appears 0 times with data, and 1 time, I guess, this dimension, say it appears 2 times with the word large and 0 time with the word data. And digital appear 1 time with the word data and 0 time with large. Information appears 6 times with the word data and 1 time with the word large. So when we plot them, the vectors, in terms of like this dimension of data and large, we can see that the angle between information and digital is smaller than the angle between information and apricot, for example. So this cosine is what we normally take to this cosine similarity is what we normally take to measure how similar are 2 vectors of word representation. So in this case, we see that cosine similarity between information and digital are higher than between information and apricot. But these matrices are really, really huge because just now the context, right? The columns can be as many as the number of words in your vocabulary. And not only that they are huge and long, they are also sparse. Most of the elements are 0. So it matters when you need to store them. It matters when you need to use them to do some other, say, machine learning processing on them, because the sparse features means that most of the elements are 0 anyway. So why are we using them, right? So the alternative to that is called the dense vectors of word embeddings. So dense means we have shorter vectors, and we have dense, that means most elements are non-zero. And why is it better to use dense vectors? First of all, it may be easier to use as features, right, in machine learning algorithm, because with less features, you have less weights to tune. With less weights to learn, you will need less amount of data to tune them, right? And then not only that, they may also generalize better than if you store like the explicit counts of how many times this word appear with that word. For example, between car and automobile, they are synonyms, but they are in the context, context matrix just now, there will be two different columns. So a word that appears with car as a neighbor and another word that appears with automobile as a neighbor will have two different factors in this case, because the car and automobile are two different columns. So they are not, they should be similar because they are synonyms, car and automobile, but if you use that large vector where each column is a distinct word, then you won't be able to capture the synonymy. While with the denser matrix, car and automobile might be just one column in that matrix. And so they might be able to generalize better in that sense. But in practice, they work better. So there's a lot of dense embeddings you can download. So for example, probably the most famous one is Word2Vec, the one that start this whole idea of using dense vectors, and then FastText, and then GloVe. So you can actually download them, and they are already pre-trained. So each word already has a vector, and then you can do many things on that vectors. The Word2Vec particularly is very popular, probably because also they are the first one, and very fast to train. And the code is available on the web. But the idea is, unlike the sparse matrix just now, the Word2Vec vector are learned through predicting rather than counting. So what does it mean by predicting? So instead of counting like how often each word appears near the word apricot, just now, like the context, term context matrix, we just train a classifier on this prediction. So we want to say, okay, I want to learn the vector for apricot that makes it useful for predicting what word will appear nearby apricot. So that question is actually, we don't care about it. We just want to train this classifier to do that prediction so we can use the weight that we learn to as word embeddings. So these features that we learn, like these embeddings that we learn, will be the word embedding of the word apricot. So it will be good at to use to predict what is nearby apricot. So the brilliant insight behind this idea of doing predicting instead of counting is that it's still the same as before. So you can still use text as your training data. So you don't need to label them, because just like counting, you just need to count, right? How many times this appear with that. In this case, you also don't need to label because you know what words are nearby apricot. So the words that are near apricot, they act as the gold answer to the question whether or not this word is likely to show up near apricot, because we saw it, right? So if it's the word pinch, yeah, it's nearby. The word data, maybe not, because we've never seen it show up near apricot. So these are like the positive and the negative examples. We don't need to label anything. Our text can be our training data. So this nearness can be defined as words that basically appear within some window size, say C size window around apricot. And so no need for hand label supervision. And we can just train the embedding without any supervision, just based on how that word is being used in the corpus. So the properties of embeddings are interesting because they reflect what what the corpus is actually saying about this word, right? So if we take like the word Hogwarts, and then we just train an embedding for Hogwarts by looking at some small size window around it, then it will find like that the word that have similar vectors as Hogwarts are things like Sunnydale or Evernight, which is two different types of school. So they are the same kind of type, like the same, well, basically school type. And then if you take a longer window size, then it's basically seeing things outside the context of school itself. So that's why the words that are nearby Hogwarts, when the window size is longer, is words like Dumbledore, Malfoy, or Half-Blood, like things that are not the same type but are related to Hogwarts. And then there are also other things that are interesting about these learned embeddings. Another thing like the geometrical property of the embeddings is that it can capture like this relational meaning of the analogy between words. Say, if we plot like the vector of man and the vector of woman in the space, and we find like the translation between them, we see that like man and woman has the same translation as king and queen. So like if we take the vector of woman minus the vector of man, we'll get the same as taking the vector of queen minus the vector of king. Or in other words, we can say king minus man plus woman equals queen. Or Paris minus France plus Italy is equal to Rome, because Paris and Rome has the same relationship as France and Italy. So these are the geometric properties that are interesting from the embeddings, and it's basically based on the idea that the word king and the word man and the word woman are surrounded by the same kind of words, right? So when we talk about man, maybe it's using he. When we talk about woman, we are using she. The same thing with king and queen, you know, he and she. So there is similarity in their geometric relation in this word embedding space. And that's not only that, like man and woman, uncle and aunt, nephew and niece, brother and sister, sir and madam, they all have almost similar kind of relation between the word vectors. And also not just like nouns, but there could be like different adjectives, like slow to slower to slowest, short to shorter to shortest. They have similar relational translation in the embedding space. And like I mentioned, these geometric structures not only appear like in English, they also exist across languages. So if we look at the Spanish and the English space, we can see that the word horse in relation to the word pig and in relation to the word cat are similar in the two spaces. So this can be exploited then to do machine translation, right? Because if we know how horse is related to pig, like there are difference, for example, in their vector representation, we can use it to predict where the pig is in the Spanish embedding space. And then, sorry, there is some. Sorry, there's some background noise here. So, and like going back to this cross-lingual geometric similarity, we can use this similarity to then align two spaces that are in different languages. So say you have words in language X and words in language Y, right? Here we have cat, we have gato, for example, car and auto, and so on and so forth. We can use the similarity between their geometric space to learn a mapping to map the space of the word embeddings in X to the space of Y, right? The embeddings of the words in language Y. So one such function could be a linear function, which just say that I apply this function W to X, I will get back its translation in the language Y. So we can learn this W basically. We can compute how to project words in language X to words in language Y by looking at, for example, cat and gato and car and auto, and map cat embedding to gato embedding and car embedding to auto embedding as some kind of examples to learn this mapping. And then once we learn W, we can apply to any other words in X to get its, say, feline here, to get its corresponding projected embedding in language Y. And then we can use the projected embedding to find the translation between, say, feline to felino, for example. So we can use, say, like k nearest neighbors to find, okay, for word X, once we apply the mapping, we got some vector, and then we look for a word in Y that has the most similar vectors to the word, the vector of W times that X. So there's a lot of like, I guess, works that have been done on it. And this is one kind of survey of these cross-lingual models of word embeddings. But then people carry it further, right? So just now, maybe what if we don't have any seed to help us learn the mapping? Say we don't have any cat, gato, car, auto correspondence, and all we have is just all the words and their embeddings in language X, and all the words in their word embeddings in Y, right? So, and the reason being that this parallel data is sometimes hard to obtain, especially when the language is low resource. So what happens is that sometimes there's not even dictionary that we can use to learn this mapping. So what happens then? So there are these works on doing unsupervised alignment between spaces. So for example, here just now we saw there are words and their embeddings in language X, and there are words and their embeddings in language Y. So what they do is just learn this adversarial training that tries to map this embedding space to this embedding space. So like this W is trained using some unsupervised adversarial training. And then once we do this, so the adversarial training is, I will speak about it after this slide, but once we are able to sort of like align these two spaces, then we can proceed with the previous method. We just use like words that are frequent in both languages and are mutually nearest neighbor in this space, in this aligned space as seeds, to then learn to refine this mapping W. And then once we finally refine the mapping, the W, we can use this W to then translate all the other words in this space. So the adversarial training is basically consists of two models that try to be adversarial to each other. So one is called generator and the other one is called discriminator. Basically what the generator is doing is it tries to learn the mapping, try to align the two language spaces such that it will fool the discriminator into thinking that, these words in X, after I apply this W that I'm learning, the discriminator won't be able to distinguish between, real Y and the fake Y, which is W times X. So it will believe that like this W times X comes from the same distribution as Y. So basically that's what the generator is trying to do. While the discriminator is trying just to do its job. So being very good at discriminating between the words that come from language X and the word vectors that come from language Y, because they should look different, but the generator is trying to do the opposite. So that's why the two of them are in adversarial training to each other. And then and surprisingly, it works to some degree, right? So this one is with the supervision. So you have some seeds and you learn the mapping, right? You have some seed dictionary that like cat and gato and car and auto just now, and you learn the mapping. So for like languages like French and German, this can like be really good at capturing the mapping between the two languages, because also they come from the same family. But like for Russian or Chinese, because they come from different language family than English, the performance here is smaller, right? This is the precision at 1. That means once I transform the word X to the space of Y, I will look at its closest neighbor in Y. And if that word turns out to be the correct translation, then I got some score. So this is precision at 1. And if we look at Russian and Chinese, also the unsupervised method doesn't perform as well as the supervised one. But for languages that are close to English, they are pretty good at mapping, like say English to Spanish or English to French or English to German. But yeah, so that's all I want to talk about the geometric perspective of the embeddings. But I want to highlight this last thing, that not only we can learn it to do translation or or solving the analogy like in a TOEFL kind of question, but also because they carry meaning that is they absorb the meaning from like corpus, they can be used to study changes in how these words are used across time. So for example, looking at the word vectors in say the year 1900 versus the year 2000, and then for example, comparing the vectors say of particular word, we can see how they differ, like based on the dog in 1920, what kind of neighbors are close to dog in the year 1920 versus what kind of words are close in the vector space of dog in the 1990. So this based on like this Google Books data that has books all the way back to the year 1500, but all the way to 2000. So in this work, they just take 1850 to 1990, but actually the books itself, in Google Books data range from 1500 to 2000, 2008 or maybe 2012 now. So you can see how the word itself changes the changes in terms of its nearest neighbor vector, nearest neighbor words in the vector space, right? So the word gay, for example, was closer to daft or sweet or pleasant, and then now it's more used in the context of like this LGBTQ, right? And then the word broadcast, at the beginning it was like broadcasting seed, spreading seed in the farm or things like that, and now it's more like close to the word radio and BBC and stuff like that. The word awful a long time ago is actually used to describe something majestic, because it's like full of awe, right? But then in the 1900s, it starts to acquire other meaning that means horrible or terrible. And now it's getting back its original meaning. So now you can say things like awfully weird, which means wonderful or things like that. So we can see how the word in terms of meaning itself changes over time. But the not so good things is that they also capture biases in the corpus. Okay? So for example, we can use the analogy just now. Paris is to France is like Tokyo to Japan, right? Because Paris and Tokyo are the capital city of these countries. But then you can ask the same thing. Father is to a doctor, is mother to, I guess the answer, like the closest answer to this analogy in the word vector space is nurse. So here we can see that there is maybe some bias with respect to gender or other things. So, or ask man to computer programmer is like woman to the word to vec will answer homemaker. So, yeah. So, and then we can also see how that can, carry over to like names, even, for example, African American names. When you take the glove is one of the word vector that I mentioned just now, like word to vec, glove, fast text. So you can see that in the using glove vectors and finding the cosine similarity of the word Leroy, like finding which adjective words are closest to it. You see that Leroy and Shaniqua are closer to things that unpleasant words versus like European American names. So the embeddings, basically, because it's created based on the corpus, and the corpus itself, like the text we produce, might contain biases. They absorb these biases, and I think to some degree, maybe even elevate these biases. So, but sometimes the biases are not biased because they are produced by text, but it could be because they reflect some historical I guess, fact of that time. For example, the cosine similarity of the word embeddings during some decades, like for occupation like teacher, are closer to female names because that could be correlated with the actual percentage of women being teachers in that decade. And for example, also like these competence adjectives toward men. So the word man has closer cosine similarity to these words than the word woman. But this bias is slowly decreasing, which I guess shows that over time, people use these words more equally between female and male. And you can also say, okay, how about other names like different ethnic groups? So there was this Princeton trilogy experiments that track people's attitudes towards Chinese ethnic groups, right? To see how they score the names of these Chinese names to adjectives like industrious, superstitious, nationalistic, and so on and so forth. And using word embedding at this different period actually correlate when you look at the cosine similarity to these adjectives, the cosine scores correlate with these human ratings. Specifically in the year 1910, these are the words that are close, the adjective words that are close to the Chinese names, and then 1950 and then 1990. So you see there's some changes in the different stereotype, right? Maybe a long time ago, it was like more like this othering adjective, which is probably because there was some, during that time, that period, there was some ban of people coming from China to US or things like that. But now it changes, but still at the same time, there's still some bias, I think, associated with these names. So in summary, I guess I want to end by saying that this embeddings is like the way we can represent meaning of words, and they are more fine-grained than just using symbols like a bunch of characters or some numbers. And they capture things that could help us do some analogy or similarity. Just, you can download, say, the pre-trained embeddings and use cosines, and you can use it to do machine translation across languages, even when there's no data that to start with, right? Like just now using the adversarial training and stuff. And there are different types, like the sparse models, just counting or using TF-IDF, or the dense models where you, instead of counting, you're predicting like word to vec or glove. And they're useful in practice, but know that they encode gender or cultural stereotypes from the text itself. So that's all I have. And thanks everyone for listening. And yeah, if you have any questions.
Okay, so we can take questions now. I see one question in the chat already. I'm wondering how debiasing might work in practical applications, since the more text we use, old and new, the better the embeddings, but also the bigger the scope for biases.
Yeah, so there are many works that have been done to debias the word embedding. So one work is actually from BU itself, from Venkatesh group in computer engineering, right? So they are the ones who start, I think, one of these method to debias word embeddings. The one that comes up with this man is to computer programmer as woman is to homemaker. So what they are trying to do is like, you know, sometimes bias are okay when it comes to like mommy versus daddy, or girlfriends versus boyfriends, or grandmother versus grandfather. They are like, because you need to use different words for man and woman, right? So they also under this line, they are this okay to be different, but above these lines there are words that shouldn't be different between, like shouldn't be closer to female than male. So what their method is trying to do, and you can take a look more closely at the paper itself, is that they try to collapse these words that are above this line to the center line. So like words like beautiful and words like brilliant, they shouldn't be close to just one gender over another, or maybe I guess what would be interesting here? Housing or busy, or I don't know. I guess trisemester is fine, but yeah, yeah. So that's the it's an open research area, I guess. Yeah, because at the same time you want this bias, but you don't want the not so good bias, right? So yeah. I hope that sort of answers the question. And you can take a look at the actual method they use to debias words in this paper.
Our next question is about the unsupervised results page. I think there was a slide on that, and says, why are some results highlighted and some others are not?
I think they are because they are either like statistically significant or not, I think. Yeah. So like if the difference is statistically significant or not, but I think no, this one is just like which one is highest. Yeah. So here the highest one is through the unsupervised method, surprisingly, for Spanish and French. English to French translation, but French to English is better to use some supervision. So I think these are bolded, means the highest result that can be obtained using the different methods.
Great. And then another question here is, are these embedding algorithms randomized or deterministic, and does randomization make a difference?
I think they start from random. So when you learn the word to vec, for example, let me see, I have the slides for word to vec. So they start with some random numbers as vectors. See. So yeah, they start with some random parameters, random weights, and then they during the training itself, because they have some positive and negative examples, right? So for example, for apricot, where is the example? Yeah, so for apricot, positive examples are words that appear within some window size of it. So like tablespoon, of, preserves, or, while the negative examples are sampled from all the other words in the vocabulary that doesn't appear near apricot. So like apricot, aardvark, these are like negative examples. So you start with some random weights, and then while training, you are trying to push, basically you want to maximize that if two words are neighbors, their embedding should be, the cosine of their embedding should be high, And when they are like negative example, then their cosine embedding should be low, so they would be classified as negative, and this guy will be classified as positive. And basically, during this training, when you are trying to modify T and C, they start with random. But what happens is they are during the training, you try to push T and C such that, you know, when apricot and jam are neighbors, the two numbers should be close, should be similar than apricot and aardvark. So they are updated as you train the classifier. So using some method, you can do gradient descent, for example, and logistic regression for the classification. You start with some random number, and then you take pairs of words that co-occur as positive example, pairs of words that don't co-occur as negative example, and then you train the classifier. And during training, you slowly adjust this random that starts with random embeddings to improve your classification performance. And then once you finish with the training, like your say validation accuracy doesn't improve, or you know your accuracy doesn't improve on the validation set, you can throw away the classifier and then you can keep the embeddings. So yeah, it starts with some random number and is tuned during training.
So Derry, can I ask a question that maybe steps us back a little bit? So as a Did You Know You Could seminar, I'm hoping that people who come will feel like they can when they leave. And it looks like there's a lot of depth and expertise that would be needed to do this. Where would someone who wants to start doing this dig in? If you saw from the beginning of the audience, everyone said most of them said that they didn't have much, and you pointed to the books, so that's great. What would be sort of the steps that you would tell someone who had sort of a starting corpus that they wanted to work with, just to start getting familiar with things?
Yeah, so you can take a look at these pages. Actually, they have the codes that you can run on your corpus to get the embeddings from your corpus. So there are also libraries. If you are familiar with Python, for example, GenSim libraries that you can use very, very easily. You know, you can give it your corpus, and then you can call a function from this library to train some embeddings of the words in your corpus based on your corpus. And they also provide pre-trained embeddings that were already trained on, say, Wikipedia corpus, and you can download them. So there are many ways to use it. You can train your own word embeddings using the code, or you can just use the vectors that they already produce. So yeah, but to if you want to know the inside of the code, then you have to, I think, learn first machine learning to understand like logistic regression at least, and like gradient descent. Yeah.
Great.
So that will.
Hi, Professor Wijaya. Thank you so much for your presentation. I think this is really interesting, and I can already think of like applications in political science already. I'm just wondering how, because you had a slide that you said you compare like Chinese with English. So I'm wondering how you could do that, because Chinese is such a different language from English. Like, are you using pinyin, or how are you doing that?
Oh, which one? Like the unsupervised alignment here? Yeah. So what they do is they train two embeddings. So one is trained on English corpus, and the other one is trained on Chinese corpus. And then what they do is you can start with some dictionary, if you have, right, of Chinese word and its English translation, to help learn this W, the mapping between the two spaces. So in this case, say if I know, if I have already some dictionary that car is auto and cat is gato, then it could help me learn this W, which is basically aligning these two spaces. So like this. And then once you align them, basically you can use the nearest neighbor to see that, you know, okay, so this gato is cat, and this say car is auto, and this is feline is felino, or things like that. So, and deep is profondo and things.
So Derry, I'm wondering if maybe the question was asking a little higher level, in the sense that, like, for example, you know, the Romance languages all have very similar root structure, right? You know, Italian, French, and all that. So you might sort of expect it to be an easier task, whereas you know, much more fundamentally, English and Chinese differ. Do you see that? I think there was a question about whether the dictionary you're using is a particular one. And I think there was also maybe a question that was sort of just, do you see that? It seems like it should be a harder task. Is it actually when you see it, or somehow all magic happens and it isn't?
No, it's a harder task. If we look at the performance, even when we use dictionary for to learn the mapping between English and Chinese words, the precision at top 1 is very small compared to like English and French, or German and English. So yeah, the similarity between languages matter, and that is reflected in the how much performance wrangling the embeddings can give you. But
have people done this like between Asian languages that have some root structure to them, as opposed to across Eastern Western? And do they see higher similarity?
So across, like, between 2 Asian languages?
Yeah, that I'm not sure which would be an appropriate pairing that would have more similar structure, but
yeah, I guess for languages that are the same family, we do see that there is it's better, just like English and French, or English and German. And more recently, I think maybe I should like show this. There are language models that have been, let's see, let me share my screen, that have been trained on many languages. So you can take a look at if you search for multilingual bird, for example, they are created, so they train one model on 100 languages. And not only to map the words, but also sentences in these languages to the same space. So they have like multilingual, and they have the just on Chinese, for example, and they see that, you know, for like for different type of tasks, for example, this is a natural language in I guess entailment task, where given 2 sentences, you want to say whether they are hypotheses, or whether they are contradiction, or whether they are neutral to each other. So when you use, for example, this multilingual bird, and you can see that there is some improvement. I guess this
it's interesting. There's a comment right there where you were, the translate train, that seems to be addressing some of what C's question was too, right? They're saying that the dependency, it's that bold underneath the table, right? The dependency, it was impossible to quantify how much lower accuracy compared to due to quality of machine translation versus the learning. Yeah.
Yeah.
Fascinating.
Yeah. So this is a very interesting area, actually, because even in machine translation, a long time ago, we want to believe that all languages exist, you know, have an interlingua between them, right? No matter how distant the languages are. And I think with this, you know, embeddings, now we start to see that this is possible, that interlingua is possible. So, but how much? Yeah, we are still pushing towards the towards the ability to translate even distant languages to each other. But yeah, but these models help, I think, as like a pre-training step before you use it on like downstream tasks.
Fantastic. Well, this is really excellent.
Yeah, beside this one, now there is another one that is better, they say, for multilingual models. It's called XLM Roberta. So the nice thing about all these language models is that you can input a sentence or word to it, and then it gives you the vector. And then you can use these vectors to do like many things like cosine similarity and all the stuff. And they are all available actually through these libraries these Hugging Face libraries that make all these models that were very hard to train, right? If we want to train it ourselves, we can't, because they require a lot of GPUs or TPUs, but they make these pre-trained models available. So people can just use the models that are already pre-trained on like this big Wikipedia and books corpora, and you can use it to do other things. Like you can use it to do machine translation or stuff like that.
That seems super useful for people who maybe don't want to really dive into the guts and either redevelop or whatnot, but really it's their broader scientific task or domain area task that they're interested in. They want to kind of get things going together quickly. So thank you, really useful.
It's good to know maybe Python, because then once you know it, then you can just like use this library. Yeah, it's very, very cool. I think it makes research on deep learning more, I guess, attainable than before. Yeah.
Right.
All right.
Thank you.
Thank you so much for a fantastic talk, and thank you to everyone who attended today. I'd also like to thank the Hariri Institute for allowing us to come together and supporting the logistics of the event. I'd also like to encourage everyone to sign on to the Hariri Institute website and look at the other talks that are in this series. So we have another talk coming up next Thursday, which is about, did you know you could organize your software workflow with GitHub? So thank you all for joining. Please check out the other talks in the series, and hopefully see you next week.
Thank you. Bye.
Thank you very much.
Thank you.
Yeah.